Okay, so in section 1.6, we're going to be looking at applications of linear systems. We're just going to look at a couple of applications, in particular chemical equations and flow diagrams. Okay, so we're going to start off with a relatively simple equation, chemical equation that you might have seen in a chemistry class or somewhere along the way. If I take H2 and O2 and I merge them, I get H2O. Now, you might be familiar with balancing chemical equations, getting the right number right. I've got two hydrogens on both sides right now, but right now on the left-hand side, I just have two oxygens, but on the right-hand side, I just have one. Okay, so we can use linear systems to help us with this process. Okay, so I can think of this hydrogen molecule as a vector. It has 2 hydrogen and 0 oxygen. And I can do the same thing here with those oxygen molecules, 0 hydrogen, 2 oxygen. So I need to keep the same order so that it works. And then I want that to yield this H2O molecule, which is going to have 2 hydrogen and 1 oxygen. Okay? And so as you look at that, it's actually a linear system of sorts. Okay? So I need that to balance. So I can turn this into a homogeneous system by bringing this one over to the left-hand side. Okay? So I can make a homogeneous system, which I can represent with a matrix. I've got 2, 0, 0, 2. And then when I bring this one over to the left-hand side, it's going to be -2 and -1. Okay? So ultimately what I have here is then I have a matrix equation with 3 variables, x1, x2, and x3. And those 3 variables are my coefficients in my chemical equation, x1, x2, and x3. Okay? So I can use that, and then that is going to be equal to my 0 vector for my homogeneous system. Okay? So I can solve this system. Okay? So I'm going to take this vector here, 2, 0, 0, 2, -2, -1. I've got my augmented zeros, and we are going to then row reduce that. Use your calculator, use your favorite method to do this. 1, 0, -1, 0. Then I'm going to have 0, 1, -0.5, and 0. Okay? And so I can write the solution set here. I've got x1 is equal to x3. Again, when I move that -1 over to the right-hand side, it's going to be positive. Okay? x2 is going to be equal to 0.5 x3, and then x3 is free, so x3 is just equal to x3. Okay? So I could write that in vector form or in parametric form. That's going to be 1 copy of x3, 0.5 of x3, and 1 copy of x3. So that would be my solution vector. Now, if I look back at my chemical equation that I started with, I can't really put 0.5. I can't have half a molecule, okay? So what I'm going to need to do is I'm going to need, in order to figure out these values, I'm going to need to multiply that by 2 to get rid of that fraction, okay? So this is going to become x3 equals 2. So if I use 2 times 1.5 and 1, I'm going to get a vector of 2, 1, and 2. Okay, so I can use 2, 1, and 2 then to write my equation. It's going to be 2H2, because again, x1 was my first spot there, plus just 1 copy of O2 is going to yield 2 copies of H2O. Okay, so that's a pretty simple equation to work with. We can complicate it further into some 2-dimensional and 3-dimensional looks, but ultimately you just set up your system using each line, each row represents one type of atom. So you've got hydrogen on the top row, oxygen on the bottom row in this system. Okay? And then you turn that into a homogeneous system and determine a valid solution. Okay? Any valid solution will work. We usually try to keep the numbers as small as possible, but you could actually multiply all these by 2 again, and you would still have a balanced equation. What you can't have for molecules, though, is a fraction. When I get that 0.5, I've got to take care of that in some fashion. Okay? So let's look at another molecule here. I've got C3H8. We're going to add that to oxygen, O2, and that's going to yield CO2, carbon dioxide, and water, H2O. So now I have 3 different types of atoms. I have carbon, hydrogen, and oxygen. Okay, so my first vector here, I'm going to just go in the order. So carbon, hydrogen, oxygen, okay, 3, 8, 0. Second vector then, oxygen, so I just have 0, 0, and 2, Remember that went carbon, hydrogen, oxygen. So I'll write that here, CHO, because you got to keep that same order for each vector. And then my third one here, carbon dioxide, I have 1 carbon, no hydrogens, and 2 oxygens. And then the last one is water. I have no carbons, 2 hydrogens, and 1 oxygen. Okay, so I can turn that into an augmented matrix. That's going to be 3, 8, 0, 0, 0, 2. Remember, I'm bringing these over to the left-hand side of the equation, so this is going to be -1, 0, and -2. Bringing these over, so this is going to be 0, -2, and -1. Okay, remember that is augmented to be a homogeneous system with zeros. Okay, I will start leaving off these zeros in some problems in the future, but just get the idea of homogeneous, so we know that that is equal to 0. Okay. And now I row reduce that. Okay, I'll show it to you in the calculator here. So I've got a 3 by 5 matrix now. So I'm going to go second matrix, go to my edit menu, turn this into a 3 by 5 matrix. Okay, 3 by 5 matrix. Typing in my matrix, I have 3, 0, -1, 0, and 0. Next, I have 8, 0, 0, -2, and 0, 0, 2, -2, -1, and 0. Okay, then I can go back to my home screen and I can do RREF. Okay, so if your last command was RREF of matrix A, you can just hit second enter and it'll bring up that last command that you entered on your calculator. Okay, so I see what I've got there. 1's across the diagonal there, and then I have a 4th, 5/4, and 3/4. Those are all negative. Okay, so let's write down that matrix that we found when we did the row reduction. So I've got 1, 0, 0. This was -1/4, -0.25. 0, 1, 0. That's -5/4, -1.25. And then 0, 0, 1, that's going to be -3/4. And then I have my augmented row, my augmented column, I should say, of zeros. Okay, and so as I look at this, I can write my solution. I have x1 is equal to 1/4 x4. Remember, go by your columns, x1, x2, x3, x4. x2 is going to be equal to 5/4 x4. x3 then will be 3/4. Again, it'll be positive when we move it over to the right-hand side. And then x4 is our free variable, so x4 is equal to x4. Okay, so as a vector solution, right, that would give us 1/4, 5/4, 3/4, and 1. But we know we can't have fractions in these chemical equations. So I need to multiply by 4 to take care of that denominator. So my resulting vector here is going to be 1, 5, 3, and 4. Right? That is that vector multiplied by 4. Okay, so 1, 5, 3, and 4 are going to be the values that we put into our chemical equation that we started with here. So 1 is the first one, x1. So 1, 5, 3, and 4. So 1 C3H8, 5 O2s, 3 CO2s, and 4 waters. So 1, 5, 3, 4 is our solution there. Okay, we can double check this. I have 10 oxygens here. On this side, I have 6 oxygens and 4 more oxygens, makes 10. I have 3 carbons. This side, also 3 carbons. I have 8 hydrogens. This side, 4 times 2, also 8 hydrogens. So that equation is balanced. Okay, so you just have to make sure you keep your atoms in order, and then you solve the system and write the solution set. Then you want the smallest integer values that work, have to take care of those fractions. Okay, now I have one more to show you of this type before we talk about another thing, which is flow diagrams. And this one is going to be, let me get my nice camera centered here. So we're going to have Cu, so that's copper, Cu2S plus O2, and we want that to yield copper and sulfur dioxide. Okay. So I've got copper, sulfur, and oxygen on this one. So copper, sulfur, oxygen, 2, 1, 0. Oxygen here will be 0, 0, 2. Next, I have just one copper, so 1, 0, 0. And then last, I have sulfur dioxide. That's 0 coppers, 1 sulfur, and 2 oxygen. Okay, and so then I set up my matrix here, 2, 1, 0, 0, 0, 2. Again, I'm bringing these others over to the other side, so I have -1, 0, and 0, 0, -1, and -2 for the last one, augmenting that with zeros. Okay. Simplifying that, we get 1, 0, 0, and -1, 0, 1, 0, and -1, and 0, 0, 1, and -2. Again, augmented with zeros. So I can write my solution set. My solution set is that x1 is equal to x4. Again, I bring that over to the other side, so to change that sign to positive. x2 is also equal to x4. x3 is equal to 2x4, because I have that -2 going to the other side. And then x4, because there is no pivot in this column, is my free variable. So my vector solution I'm looking at is 1, 1, 2, and 1. So I don't have to multiply that one by anything. So really, I just have 1, 1, 2, and 1. So just that third variable, that third column, needs a 2. So put that 2 in front of the copper, and we're good to go. We've got 2 coppers each side, 1 sulfur each side, and 2 oxygens each side. So that's another relatively straightforward one. So set up that system, reduce, row reduce, solve that system, and you should be good to go. Okay. So next thing we're going to look at is called a flow diagram. Okay. So in a flow diagram, we have something that looks like the following. So I have 3 points here, which we will call A, B, and C. I got A, B, and C. And I have a flow that comes into my system from the left of A. It splits then, go up to B. Okay. Perhaps it goes down to C. Okay. Off of B, it also goes out of the system. Okay. It can also come in from this side of C. And then between A and C, it flows from C to A. So we have that loop going around. We can go out at B. We can come in from C or A on either side. So imagine you have some sort of pool or sewer system, tidal system that moves water around, or moves sewage around, whatever it might be. Okay. Now we have some different things that happen here. So coming into my system at A is my variable x1. Moving along, that next one is my variable x2. Okay, sliding down is x3. And then moving from C to A is x4. Okay. Now up here at B, we always have 100. We don't know what the units are here. Maybe it's a cubic feet, cubic centimeter, something like that. We have 100 going out, and coming in at C, we have 80 going in. Okay, so we can use this diagram to establish a system of equations. Okay, so at each of these points, we know that, basically law of conservation of matter, conservation of energy, that type of thing. At each of these points, the flow going in and out has to be equal. Okay. Also, for the whole system, the flow has to be equal. Okay, so we're going to have 4 equations, which is good because I have 4 unknowns, x1, 2, 3, and 4. So we're going to have the system, and we're going to have points A, B, and C that we can determine the flow, or an equation representing the flow at those points. Okay, so for the system, I have x1 coming in, I have 80 coming in, and I have 100 going out. So I'm going to make 2 sides of my equations here. I'm going to have an in and an outside. So coming into the system, I have x1 plus 80. That's equal to what's going out of the system, which is 100. Okay, at point A, I have x1 coming into point A. I also have x4 coming into point A. So x1 plus x4 is coming in. Going out is just x2. Okay, at point B, we see I have x2 coming in. That's the only thing coming in. But I have a couple things going out. I have x3 going out, and I have 100 going out. So x3 plus 100 going out. Okay, at point C, I have this arrow for x3 coming in. I also have an arrow for x4 going out. I also have this 80 coming in, okay? So coming in, I have x3 plus 80, and going out, I have x4. So now I have 4 equations and 4 variables, so I can set this up as a system, okay? So I want to make sure I get the constants to the right-hand side and the variables to the left-hand side, okay? So my system then, first equation, I've got x1 on the left. Okay, I'm going to move the 80 over to the right. 100 minus 80 is going to leave me with 20 on the right. Okay, second equation, I've got x1 minus x2. I'd like to keep them in order so I can keep it straight. And then I have a plus x4. And that's all I have there, so I'm just equals 0 at that point. At B here, I have x2, but I bring the x3 over, so x2 minus x3, and that's going to equal the 100. That's still over on that side. And then here I have x3 minus x4, but now I need to get the 80 over to the right-hand side to be my constant, so that is negative 80. Okay, and so from there, I can set up a system, not a system, an augmented matrix. That's what I want to say. There we go. I can set up an augmented matrix. Okay. So my first equation, I have x1 is 1. Then I have no x2, x3, or x4, and it's equal to 20. Second, I have x1 is 1, x2 is negative 1, x3 is 0, x4 is 1, and that's equal to 0. Again, I'm augmenting this here. Okay. Third equation, no x1s, 1 x2, negative x3, no x4s, and 100. Fourth equation, I have no x1s, no x2s, 1 x3, a negative 1 x4, and that is equal to negative 80. Okay. Now, I want to take this system that I have here. Okay. X1 is actually already determined, you'll notice. X1 is 20, okay? But I can take this system and I can row reduce it, okay? Use your favorite method for row reduction, right? This is not a too bad one to reduce because you can get zeros down below real quick. You'll set up a 1 here without too much trouble. You get 1s down the diagonal without too much worry. But we can use our calculator again. So I'm going to do a 4 by 5 matrix here. Those are my dimensions. I've got 1, 0, 0, 0, and then 20 for the last one. 1, negative 1, 0, 1, and 0. 0, 1, negative 1, 0, and 100. 0, 0, 1, and negative 1. And that's going to make negative 80. Okay. We're good to go on that. Okay, and we're going to then reduce our matrix using RREF, and we see our solutions here. So notice x4 is a free variable here. Okay, so let's see what we got. We got a matrix of 1, 0, 0, 0, and 20, 0, 1, 0, negative 1, and 20, 0, 0, 1, negative 1, and 80, negative 80, and then all zeros along the bottom row. Okay. So using that result now, I can write my solutions to this system, right? I'm going to have the x1 is equal to 20, no matter what. x2 is going to be equal to x4 plus 20. x3 is going to be equal to x4 minus 80. And then x4 is going to be free. Now, there are some limits on x4, though. So we like to say most of the time it can be anything. And so if it can be anything if we just have an abstract system, which we're dealing with a lot of the times. But here in these applications, we don't have an abstract system, okay? The amount on x4 in my flow diagram here has to be positive, okay? I can't have a negative thing there. I've got positive values throughout here. So as I look through, x1 is always 20, okay? So no problem, that's fine. x4 plus 20, that'll stay positive, not an issue. But x4 minus 80, x4 here has to be greater than or equal to 80. We could have 0 on that flow. That would be allowed. Okay, so x4 has to be greater than or equal to 80. Okay, and you can find any particular solution you like for this system, right? I could have x4 equal 80. That would make x3 0, and x2 would be 100. Say you make x4 100. That's fine. Then x3 is going to be 20. x2 is going to be 120. 100 plus 20. And then x1 would still be 20. So x4 can be anything greater than or equal to 80. Okay. Now, if you look through the book, there are a couple more examples of some flow diagrams. There's also at least one other chemical equation one. Okay. There's another type of application that is discussed in the book. I do not have any problems about that in the homework assignment. So you don't have to worry about that. Those are interesting problems too. But the homework assignment is exclusively the chemical equations and the flow diagrams. So in the chemical equations, make sure you keep your atom type straight. So we went, in this one we went carbon, sulfur, oxygen, but you guys have to keep that in order. Okay, make sure you keep that in order. Monitor where your variables are, right? So if you put the columns in that order, then you need to assign the variables in that order, x1 through x4. Okay, in your flow diagrams, you should set up a system of equations using the fact that the inputs and outputs have to be equal in these flow diagrams. You should have one equation for each point in the flow diagram that's marked and one equation for the system as a whole. That should get you enough equations to solve your system, okay? And then remember that the values on that have to be positive. So if you have a free variable, you have to make sure you account for that situation later on, okay? So again, section 11.6 is a fairly short section. Nothing too different. Focuses again on the linear equations, systems linear equations we're looking heavily at here in chapter 1. Please be in touch if I can help you with anything. Contact me via email or at my office hours, and I'll be happy to facilitate what I can help with. All right. I'll see you on the video for 1.7. Please be in touch if I can help. See you then.